binary, Mr. Ryan, right? Okay, so we talk about a binary search tree. Okay, so binary search tree. What's binary search tree in one sentence, please? Anybody?
Binary search tree is a binary search.
Binary tree, but it also
A binary search tree is a binary search tree.
Wait down. Binary search tree is a binary tree, but it also has to satisfy that the nodes on the left side should be strictly smaller than the root. Okay, and the node on the right side should be strictly bigger than that. So this is the binary search tree. Look at the root. Left smaller than the root. The right bigger than the root. Eric?
Yeah.
So one thing about binary search trees is does not contain duplicates. So we cannot have these double 2 here. You know, that is not a binary search tree. Okay. And then also if I have this -1 and then this node, yeah, 8. Is this a binary search tree? Why is that?
Because 8 is not smaller than 2.
Exactly, that's a pitfall, yeah. So every node on the left should be smaller than that, right? So this is bigger than that, but that has to be smaller than 2, okay? So I can put 0. So why do we have these? Because if we perform what kind of order, then you become in order. Yeah? Do you get it? So we want to do this binaries, we want to perform this in order traversal, yeah? In order. If we perform this in order traversal, and then we'll get the sorted list, yeah? For example, the in order traversal is visit the left tree first, we visit the left tree, left search left, and then we visit the root, and then we visit the right tree, right? This is the pseudocode for the in order traversal. So look, if we visit the left tree, yeah, first, yeah, and then we visit the root. So what do we get here? Is -1, 0, 2, 3. Okay, so it's in order, right? Got it?
Yeah.
Okay, so today's task, we want to find, we were given this BST, we want to find the k smallest number in the BST. Yeah? We want to find out the case, for example, this given this, and then the k is the one index. Yeah? If it's k equals 1, then the first one, then the smallest, yeah, the first smallest number is -1, and when k equals 2, then we should get 0, right? Because 0 is the second smallest, right? Get it?
Yeah.
Any idea? What did we learn yesterday? We learned about turning this into a greater tree, yeah? Yeah? 0, -1, 2, 3, yeah? Yeah? That's what we talked about yesterday. But today we want to find the k smallest number in a binary search tree. Anybody? Eric? What's your thoughts?
Doing the same thing.
Yeah, same thing. Yeah, exactly, same thing. Perform this in order, right? And then we talk about the yield thing, yeah? What's the yield thing, right? What's yield? The iterator.
Promise.
Yeah, promise. Yeah, exactly. It's like I promise you I will return this, but that's not the time yet. Yeah, when we get it. So why do we need the iterator for the yield for in this case? Because the tree might be big. The total number of nodes might be 1 million, right? But if you're asking me like what's the 10th smallest number, do I have to traverse all the tree? Right? Do you get it? So look, if there are lots of nodes here, if the total nodes is 1 million, and all we want to know is the third smallest number in the binary search tree. So if this is the case, I don't need to travel. I don't need to visit 1 million, right? Because this binary search tree give us the sorted list. All we have to do is visit the third one, and then that's it, right? So we can use the So it'll be better to use the iterator instead of converting. Obviously, if the node is small, right? The number of nodes is small, like maybe 100, right? So it's okay. We probably can convert everything, convert this binary search tree into a list, yeah, into a list, and then we do this k thing. Okay, I'm going to write this. Okay, so I need the eraser. So I'm going to write a few methods. Yeah. So and you tell me which one is the best. Okay, the most naive way of doing this. Right. So let's say define depth of search root. Okay. If not root, if the not root, we return an empty list. Yeah, empty list, and then we can do this. Return dfs root.left. This is from yesterday. Plus, this is the list concatenation root.value plus dfs root.right. Okay, so this is the in-order traversal that returns a list. Then we can do this arr equals depth of search root, and then we want to return the case one, so we just return arr case one. The first one will be k minus 1, right? K minus 1 because they start with 1. And first one is the index. You see? That's the most simple one, right? So the disadvantage, the pros is very simple to implement, okay? Right? The cons, the disadvantage. Okay, I'm going to talk about the disadvantage. Well, the disadvantage is what? I was just saying that if the number of nodes is too big, 1,000,000 nodes, and this method needs to visit all the 1,000,000 nodes and can put it in the list and then do this. Yeah, return the k. Yeah. So this is not very convenient, but we can improve it. We can improve it with this one. So how do we do that? So instead, we are not returning the list. We are not returning this. Yeah. Depth of search root, and we have this k here, and we have this answer. At the beginning, we set it to none. Right. So if the k is smaller than 0, we just return, yeah, because we don't want to continue visiting it. Now we want to visit the left part, root.left. Okay, and then we k minus equals 1, right? We have visited one more node. If k equals 0, then answer, we set it answer equals root.value and return. Okay, we return here. And now we can do this depth of search root.right. Okay. And then we do this depth of search root, and then we return the answer. Yeah. You see, this is a small improvement. Yeah. Everybody, come on. I'm going to explain this one more time. Yeah. We decrement this k. When we visit one node, we decrement it. If it's 0, then it means that's the node we are looking for. And then we set the answer here, right? Okay, so I'm going to write here non-local, just to use the variable non-local answer k. Okay, and then look, we visit the left tree, we visit the current node, we visit the right tree. Do this depth of search one time. Yeah. So this is simple improvement. Yeah, because that allows us to skip the rest. Okay, so BST with 1,000,000 nodes, and I just want you to find out the smallest node. Yeah? Yeah? So you just find it, right? And you don't need to find the rest, 1,000,000 minus 1 node, right? Once you find the target, do you need to continue? Because you already have the answer, why would you visit all the rest? Yeah? Simple as that. That's this part. If k is smaller than 0, then we just return. Yeah? Here. K minus equal 1. Okay? Okay. Okay, so now I'm going to write the much better one, which is called the yield function. Yeah, yield iterator. Yeah, if we're using the yield to iterator to write it, then it will be much simpler. Okay, define depth of search root. Look here, yield. Okay, so I'm going to clear if not root. Okay, probably here one thing missing is that if not root, we should return. Okay. If k is smaller than 0 or not root, we should return. Okay. Yeah, here. If not root, return. And then yield from dfs root.left. Okay. And then yield root.value. What's the money? And yield. What's next? Can you tell me what? Okay, Eric. Yield from root.left, yield root.value, and yield from root.what? Right, exactly, yeah. Root.right. This is the in-order traversal. And then we can just do this. If we have this DFS root that returns an iterator, yeah? It returns an iterator. Come on.
Yeah.
So what do we do now?
You.
So we just do this. Yeah. Return. We're using the next function. Next I for I. Next C. Okay. For C I C in enumerate. What's enumerate? Anybody?
Like keys.
What's I? I is the
Index.
index. C is the value. In DFS rule, yeah, we want to return this is the iterator, but I is the index. If I is equal k minus 1, right? So we want to find out k1, yeah. So obviously you can rewrite this using the traditional if statement, yeah. For IC in enumerate DFS root, yeah. If I equals k minus 1, then return C. Okay, but we are using a fancy syntax called the next function. Right? Next function. So what's next function? Anybody remember? Okay, next function is the returns the next value in the iterator. Yeah. Okay. So look, the range function is the generator. Okay. So we look A equals range. Yeah. We know the range. Yeah. Range 10. Yeah. Range 10 from 0 to 9. If we put an iterator here, we convert it to iterator, yeah? Then that's an iterator. Okay, so next A, what does it return? Next A.
It returns
What's the first value in the range 10?
1.
0. It starts from 0, right? Okay, it's 0. Okay, and then I do this another one. Next A, what does it return? 1.
2,
Next
3, 4,
A.
5, 6, 7, 8, 9, 10.
Okay, I'm gonna keep writing here. Next A. Suppose next A now is 9. Okay, so next A, what happened?
10.
No. Come on. You already. It only is.
Eric,
Look.
I'm the best.
Come on. Yeah. Look at this range function returns 0 to 9. But now we are running out the number, so you throw the error. You have a mistake. Yeah. You have an exception. However, if I do this next A, the second parameter is the default value if the things go wrong. If I say -1, then it will tell me -1, right? Do you get it? Next, range 10. Range is a generator. I convert it to iterator. Yeah, convert it to iterator. And then every time you ask for it, you give me the next one. In the iterator, it's like a year, promise, right? The iterator, range 10, means that, okay, I promise you I will give you 10 numbers from 0 to 9. Got it? Okay, you ask me 0. You ask me 1. Ask me. Okay, you ask me 9. And then you ask me one more time. But I'm running out of number. I promised already 10 numbers. You ask me 10 times already. And you ask me one more time. What do I do? I was screwing. Yeah? I don't have more numbers for you. That's a promise, yeah? And then, but if I give a second parameter -1, yeah, Eric, I can give a Eric and I throw the Eric to you. Do you get it? Do you understand? Yeah? Alright.
Yeah.
The range function start with 0, okay? It's not start from 1, okay? Come on,
Yeah.
it's a simple one, yeah? Then, range, one more thing, range, start, stop, step, okay? Or, range,
SSS.
start, stop, or, range stop, okay? There are 3 kinds of, you can call this range function in 3 formats. Start, stop, step. Stop does not include a stop. Like 10, you give a 10, it does not reach the 10, right? Get it?
SSS.
Yeah? Start, stop. If the start is missing, then it's default to 0. If the step missing, it's default to 1, right? Step is 1, right? Okay? Make sense?
Start, stop, step. SS.
Okay, in one sentence, what have you learned so far today? One sentence, what have you learned so far?
BST.
Binary search tree. What are we doing?
I am the best.
What are we doing with the binary search tree? What do we try to do
K
now?
smallest.
K smallest. And
K
usually,
smallest.
yeah, we're using the depth search. The in order. Yeah. Why do we need to perform the in order of the binary search tree? What do we get if we perform an in order?
Smallest to largest.
Assorted is. Okay. Yeah. That will be it for today. Bye bye.
Say bye, Chapter.
Bye bye.